Hello, good day. So today we are looking at these two questions. Okay, so here we are asked to obtain the integral of ax raised to the power n dx and the integral of a into bracket bx plus c raised to the power n dx. If we look at these two questions carefully, we'll see that the difference between this and this is that this x here is replaced by these brackets, right? So which means the application of this integration ax raised to the power n dx, we can apply the law of that particular law of integration to this. And that is that to get this one is going to be ax raised to the power n plus 1 all over n plus 1, right? Plus c. Okay? Where n is not equal to minus 1. Okay? Because if it is minus 1, it's going to be it's going to be 0 here, and that will be infinity, which means no solution at that point. Okay, that's why we usually put this. Okay, now for this particular situation, you will see that for this one it is only x that is here. Now if we want to apply the same thing to this, y will be a bx plus c raised to the power n dx. We are applying this, taking, just assuming that this one is just like x here. This is going to be what? A bx plus c raised to the power n plus 1 all over n plus 1. Now, to now complete the integration, we now need to differentiate this because it's a function of function. When we differentiate this, we get this b as the coefficients, right? When you differentiate. So now this b now, in differentiation, normally we multiply that function. But in integration, what we normally do is to divide. So this is going to be the inverse of the coefficient of x, which is inside the brackets. So it's going to be 1 all over b. That's going to be multiplied by it. So whenever we have a question like this, so when it is now a linear function instead of an ordinary x, if it is now just an x with something, with a constant, that's a linear function, right? So that means it's now a function of function, and then we have to take that into consideration. Okay, so this is now going to be plus c. It's now going to be a all over b and bx plus c n plus 1 all over n plus 1 plus c. So that's going to be the final answer. Okay, so another way of doing this is to let u represent this particular brackets. You can say let u equals to bx plus c. Okay, so I will now say the u is going to be b dx, right? That is, when you differentiate bx, you're going to get b, right? And du dx is going to be this. So the x from here is going to be the u all over b. Okay, so we'll now put everything back into the integration. So y will now be equals to a u raised to the power n. Now instead of writing the x, we write the u over b. The u all over b. Right? So, and this is going to be a all over b, because those ones, they are constants. Then u raised to the power n, the u. So this is now looking like this particular expression here. Okay? So this is now going to be a all over b u raised to the power n plus 1 all over n plus 1 plus c. Okay? So that will be a over b. Now we replace the u by what? Bx plus c. Bx plus c raised to the power n plus 1 all over n plus 1. Okay? Plus c. So this is going to be the final answer. You can see that this is the same thing as this. Okay? So this is just like a shortcut. A shortcut to this particular procedure. Okay? So we can decide to write this like this, or we do it like this. So whenever we have it, it's just for us to add 1 to the power divided by the new power, then we multiply by the inverse of the coefficients of x inside that bracket. So that's how we go about that. Okay? So this is how we carry out the integration, right? So we'll do more examples of this. So examples of expressions like this, they can come in different forms. It can be represented as bx plus c raised to power half, that is square root. It can be represented like this. It can be bx plus c raised to power 3 all over 2. It can be represented by any kind of power. You get it? So, and we'll see more examples of this later. But I believe this one is understood here. I'm trying to do a comparison for you to be able to see. That is when this one is expanded to a linear expression. Okay? Okay, thank you.